And the plan is to talk a bit about explainable AI and leading up to some of the recent work that's done at DTU, mainly in collaboration with Laura Rieger. So Laura is just about to graduate. She'll defend her thesis in explainable AI. Laura came to DTU from the group in Berlin, Klaus Robert's group, already with experience in explainable AI. So she virtually hit the ground running, and I think has some really interesting I want to share with you. Although I've now worked on this for years, and some of my own work that I'm going to explain also prior to working with Laura on explainable neuroimaging is very old. So we've been working on this problem for a long time, but still there are very, very significant open problems that I want to share also, and hope that we and maybe together we could make a stab at some of these issues. Fortunately, I see that already this morning we have several considerable talks on explainable machine learning. So maybe some of them will be solved there, but let's go to that also. So here's the brief outline, and on the right side, I have the front page of a book that was collected after a workshop some years ago and came out in 19, edited by Wojciech Zamek, Klaus Robert, and this group of people that organized the workshop. And it has both sort of forward-looking research papers, but also papers that give sort of more motivation and background, including a chapter that Laura and I authored on some of the motivations and sort of historic contributions that have been given over the last many years in machine learning. And then at the end, I'll touch on these open problems. There are two different levels of explaining machine. So at the end, we'll talk about how to actually evaluate, which is a significant issue, and that involves not the least who explanations for, so human-in-the-loop type issues. And then maybe the main issue that we'll just touch upon in this presentation, and which is on causality and causal explanations. So let's take a look at the motivations for opening the black box, as it's often referred to, and there are multiple. So now I change page to talk about trust debugging, which is very important for reference, and there's multiple dimensions also to that topic. So one is simply we want to equip our AIs to call social competence, in particular communication. Think of AI as a collaborator and teacher. And this is something that people discuss both in machine learning, but also in the cognitive sciences. And I'll give an example of what we can sort of learn from cognitive science when we design machine learning communication systems. For example, how to think about uncertainty. Another super important problem where we use explainability tools is for debugging, so at different levels, and I'll show you an example of that from a high-profile paper on medical imaging. There are also what you would call legal aspects to it. So in the European Union, we have the GDPR, and this means, for example, that all the major organizations, including universities, for example, have a digital protection officer that's a position. It's a high-ranking position in the organizations that keep track of all the GDPR issues. And one of the issues is that if people are subject to algorithmic decisions, so say machine learning tools are used in decision processes, then the subject of those decisions have a right to explanation. So in the GDPR, there's no that formulation is not there. It's much more complicated, formulated legalese. But right to explanation was formulated by Goodman and Flaxman some years ago in preparation for the GDPR. And even among legal scholars, it's sort of not completely clear what it means, whether it's functional explanation, so that you have a right to know how the function works, so the machine learning function works that make the decision on your behalf, or it's how your decision was influenced by the machine learning and so on. That's still open for discussion. There's some references at the bottom that, if you're interested in these aspects. Now, moving down this list, there are two applications that I've been involved in myself mostly, and that's different scientific applications of machine learning, in particular in medicine, where we want to learn from machine learning solutions. So we train machine learning systems from examples, and then we want to understand what they learned and how they work and so on. And this is where these causal mechanisms, of course, have high interest. So I'll try to explain later. And then there's the scientific issues related to explanation itself. So my claim is that explanation is an interesting research topic. It's certainly an ill-posed task, as I'll explain more into detail in a moment. Even the fundamental sort of questions about existence and uniqueness is not solved, or they are not solved. So let me shift the page, and I moved all the way to the end. That was not the idea. Let me just go to explainability and the objectives. I hope you see the page saying explainability objectives, second generation AI. So this is a sort of throwback into the history of AI. So going back all the way to the 80s, 90s, where the symbolic AI community developed what they call the second generation AI. And the second generation is precisely focusing on explainability. So they operated with two parallel systems, symbolic systems, so one that solved the problem and one that explained the solution. So that's, of course, one of the benefits of working with the symbolic methods is that they lend themselves more to explainability than conventional machine learning systems, for example, that work by geometry. Can be much harder to a priori to explain a geometrical solution than a symbolic solution. But in this process of defining this system, the parallel system that could explain decision, for example, for mycin, the high-profile application in biomedicine, they formulated these principles so that you find that in the Swart-Moore paper from 1993. So the four topics that they put a focus on are sort of different dimensions. So fidelity means that this parallel system must be a reasonable explanation of what the system does, representation of what the system does, as I say here. That's here. So of course, that's a classical mapping problem. So we have a map of Tromsø, and now of course the best map is Tromsø itself, right? If we want to create a system that is useful for users, it should both simplify but also still be faithful. So that's the fidelity problem. Another super important problem is to address this at the level of the user. So that's a completely open problem. I would say that very few systems have solved now, and that is to take the understandability issue into account. This explanation that you provide should take departure from what the user already knows, or the competence level of the user. Then there's the sufficiency, and that has to do with sort of the decisions that you make. If you follow the explainability rules, they should be close to the decisions made by the complete system. And then the final sort of computer science-y type issue is the costs that go into computing the explanation. So it should be relatively low overhead. It shouldn't cost more to explain than to solve the problem. That's basically the idea. So some of these have been addressed in research, and when you see these objectives, you can also ask natural intelligence. So how well do we actually do it? So now that's sort of on the issue of trustworthiness of explanations. Let's start with ourselves, right? So here's an experiment that was done by one of my collaborators in Lund, Sverker Sigström. He's a natural language expert working in cognitive psychology. And he and his co-workers, they designed this super interesting experiments on human explanations, where we can maybe learn something from. And it's published under the heading Choice Blindness, because it turns out that the humans are not always super reliable when we explain things. So in this experiment that I hope you see 4 small images, A, B, C, D. So that's a picture of this experimental situation where we have an experimenter and an experimental subject. And the experimenter shows 2 facial images, and the subject should choose one of them, the one that is more likable by that particular subject. Now, the experimenter is a magician. So what happens next is that the experimental subject chooses one of the pictures as the one that she likes the most. And then the experimenter asks the subject to explain why that picture was chosen. And in that process, the experimenter can either show the correct image or by magic tricks show the wrong image. And first of all, we're not very good at remembering. So we don't really recognize that because the magician is so efficient that we are tricked into believing that we now see the image that we chose. And then the experimental subject is asked to explain. And then Sverker analyzes the explanation. So they transcribe the explanation and then analyze it. And then they show that the explanations are at all the important dimensions, natural language processing dimensions like emotionality and so on, are identical, whether you explain the decision actually made or the opposite decision. So there's sort of a basic trust level, and this, of course, is something that we have to think about when we design systems for real users. Then let me continue sort of this historical account and show my own first visualization of a machine learning model. So that's a neural network for mind reading. So in this case, we have a brain scanner that scans the mind of an experimental subject. Now we're not asking questions to the subject, they're simply peeking into what happens under the skull. And then we have a deep neural network, a deep in quotation mark. It consists of a pre-trained model, also known as principal component analysis, and then a MLP with a single hidden layer that is carefully optimized, and it reflects training on a real data set of about 100 samples. So we have a very high dimensional model with 100,000 variables. Most of them are trained unsupervised, so we don't overfit. We can very carefully control the overfitting. Now we want afterwards, after we have fitted this model, we want to understand what it does. And this is what you see. Hopefully you see a little video running in the right side of the picture. And that's the explanation. So we asked for every location in the brain, how important is that location for the prediction of what that mind is thinking of? And this is a visual task that we monitor. So much of the activation is in the visual areas, but they're spread out activation. So that's the color part of the image. The grayscale image is sort of a reference volume that tells you where the brain and anatomy, how that brain anatomy looks for the subject. So with this tool, we immediately, when communicating it to our medical collaborators, the visualizations and also the numbers, we got to think about this issue of uncertainty that is so important, and I can see also some of the talks later this morning will address. So can we say anything about how sure can we be on that explanation? Can we trust it, basically, like we questioned the trustworthiness of the human explanation before? So I'll get back to that and also talk about how to quantify uncertainty. Before I sort of leave the examples, let me just show you another much more recent example of a deep network. So this is a very high-profile paper that on Google and Stanford published a couple of years ago. Not for brain imaging, but for another type of medical imaging where you classify skin lesions. So they used a pre-trained network, not a PCA, but a more conventional deep pre-trained network for visual recognition. And then they retrained that for training the output layers to classify skin lesions. And they also, in the paper, give 2 different types of visualization of what the network is doing. So one is sort of at the functional level, just like what I just showed for the brain imaging case from the 90s. they visualize what the representations are like, and you can see from those representations that the network solves the problem. So it groups skin lesions in a way that is similar to what the dermatologist how they would group it. So that's of course a useful part of the debugging process, that we actually trust the representation that the network has learned. They can also show how individual decisions are made. So on the left side, you have this visualization of the latent representations, how they work for all samples. And now on the right side, there are some examples of why a particular lesion is classified as it is, for example, as a malignant melanoma. So it basically shows the part of the image. So that's what we call sensitivity mapping, just like we showed for the brain before. That what are the important regions in the image for that classification that can help you to understand the classification problem and the individual decisions. So now let's get back to this uncertainty issue, and I'm going back one more time to the cognitive science dimension. So what can we say from sort of looking at how humans are making decisions and how they communicate decisions? So this is some work by Bahadur Barami. Was published also, it's a very high profile paper again, published in Science, Optimally Interacting Minds, with collaborators in Aarhus University and Trustworthy and so on. So what they show in this paper, I'm not going to detail with it, but the two subjects are looking at a very noisy image and should make decisions about whether there's a particular grading or not in the image. So it's a very high decision process. It's run roughly at a threshold. And the question is, can they now collaborate? So one possibility for collaboration, of course, is that they make a decision individually, vote on the outcome, and then make a joint decision that way. Turns out that they do much better if they also communicate their uncertainty, so that in the voting, they weigh the decision by uncertainty. That's what they call optimally interacting minds. So the takeaway message is that if we have two intelligences that are communicating and making decisions as a group, then communicating not just individual decisions, but also the uncertainty helps in the decision process, as we would expect also from basic stats, right? So they confirm that here in this paper that I can recommend you to have a look at. But this is sort of another piece of information that I would use as motivation for looking at uncertainty. So we already in the 90s were worried about uncertainty, so much before this, of course, and that was because we communicated with medical experts, and they always want to know how sure you can be of a given decision, of course. So let me just show you what so our solution was to stating uncertainty. So we used resampling, statistical resampling, something we can do for conventional machine learning. We call the principle the n pairs. So it's a split half resampling. So we basically split the set in two halves to the next page. Halves. So we do that by random assignment. So the two sets are statistically identical, train two models, and then visualize each one of them, and then compare the two visualizations. So when these models are trained on identical data sets, the visualization should be identical. So this means that if there's a difference, it's the difference is an estimate of the variance, or the squared difference is an estimate of the variance. So by this means, we can get unbiased estimates of the variance of a visualization. And you can use this also for cross-validation and so on. So you can create sort of a workflow that both gives you cross-validation type measures of performance and uncertainty, and then also for the visualization. So we use that in the NPAS workflow to optimize both performance, but also robustness of explanations, for example. So we have a two-dimensional evaluation plot, and a system is preferred if it has high performance and also have robust explanations. So in the papers at the bottom, we have a whole list of neuroimage papers where we sort of explore that to optimize different types of neuroimaging models and so on. Going back to the skin lesion problem, so we also worked on the skin lesion issue. not with physical images as you see at the bottom right here, but with something called Raman spectra that are very detailed and sensitive measures of chemical composition. And there we could compute spectral sensitivity. So for each wavelength, basically, we have an input to a neural network, and we can ask how important is that wavelength for decisions, different types of decisions. And by computing the uncertainty using this n-pairs resampling method, we can quantify the uncertainty. So we can normalize this as what we call a C-score. So normalize the importance of a pixel by its uncertainty, say something like the standard deviation. So you get a C-score, and now we can ask sort of what are the significant regions in the spectrum. And by this means, in the paper that there's a reference at the bottom again, we found some new spectrum were not known to the medical collaborators, how to make decisions, for example, again on melanoma and so on. We've also done this for EEG mind reading, and here I just want to show a quick example. I'm not going to talk about the details here. References are given below. On the right side, we have not a single spectrum, but RAM. So this is how the power distribution changes over time. So we have time on the x-axis and frequency on the y-axis in the conventional RAM. And what you're looking at, the coloring, the red areas are regions where you have high significance. So this means that the C-score, the importance for classification, normalized by the uncertainty of that is high. And at the bottom, you can see this has been thresholded. And there's paradigm subject is experience, subject to a certain experience, and that happens at the time of the red vertical. So in principle, there should be no important activation before, right? Because the classifier should only use what happens after the brain is experiencing. So this shows that there are these causality issues, that we find that some of this activation that happens before this is actually important. Now, this is a well-known problem in that particular field, in the EEG mind reading, that this happens, and it has to do with correlation in the noise. So the algorithm can use the situation in the brain, so the EEG situation that happened before the stimulus, to detect certain confounders and then subtract those in the stimulated part. So we should always be very careful when we interpret models like we do here, that it's not causality we are looking at, strictly speaking, what the classifier does in order to understand the domain. If there are questions to this issue, I'm happy to discuss that also later, of course. So if we sort of step back and sort of look at the more principles, we have now talked a lot about what you would call sort of the norm uncertainty, or aleatory uncertainty. But this field is so rich that we have hundreds of different ways of visualizing neural networks already. So this means that besides the sort of what you could say the noise that comes from the finite samples that you're working on and so on, there's a completely different type of noise also called uncertainty with the actual methods that we use to visualize. So here we show different methods that I'm sure many of you have heard, like saliency maps are the ones I've been talking about up to now, but they're also what we call guided backprop, smooth graph and GradCam, and there are Lime and so on. There are many different methods. And I say here is 100 plus. I mean, maybe even 500 plus. There's a lot of work here. So we looked at all these methods, and in neuroimaging, we have earlier argued that if we have this kind of plurality of modeling, we should try to average or aggregate the models. That will typically give us more robustness and also better understanding by looking at the divergence between the model results, understand the diversity in such modeling issues. So this is what I'm going to talk about. These are some of the recent results that Laura has produced, how we can use these aggregates to reduce model uncertainty and also understand much better the space of visualization. So here's some results where we can actually evaluate in sort of the fundamental way. So we have an image set where we have human evaluation. So we simply ask people to classify these images and also to explain what part of the image was important for their classification. So we have a chair. So what do people say about the importance of different parts of the chair? So that's what you see in this image below here, is sort of the vote among a group of people who have drawn on the image what they thought is to become classified as a chair, and the same with a zebra and so on. So here we have a kind of ground truth that we can compare with. And the plots below, without going into detail, are all these different methods, how well they correspond to the human annotations. And then the green bars are they outperform the individual methods, as you would expect, similar to ensemble methods in general. So now, when we look at the evaluation and the situation where people use this kind of system, there's a very important insight that was conveyed, I think, many times, but in particular clear way in this paper from 2019, that users really want to know about the causality of a model. So they want to answer to counterfactual questions. So a counterfactual is what would happen to this image if it looked in this different other way. So the way they formulate it here is that they say that what are the changes in an image that you should do in order to get a different classification. So that's basically the adversarial issue that is asked here. Now, that is not a question that we can answer simply by opening a machine learning model, because that would take experimentation. So that's why I'm saying that this causal issue is unsolved, because here we're simply using the model that we have to try and pose and answer counterfactual questions, and that can only be approximate. So this has been used, approaches like this has been used for evaluation in the literature before. So there's this approach that is called pixel flipping, where you simply ask, what happens if I remove the information in this particular pixel from the classifier? What happens to the classification? And if you remove important pixels, then the classification accuracy should go down quickly, right? So when you start to remove pixels according to a certain map, a certain visualization, so we remove the most important things first, then if the classification accuracy drops fast, then it's a good method, right? Because it's pointing to the salient regions. So in the Lars paper on the IRAF, we generalized this a bit, so it became more sort of like counterfactual. So we grouped pixels into fundamental regions by segmentation. So for the bird, it would be like the beak and the wings and so on. We can find by image segmentation, and then rather than flipping pixels, we sort of frame parts of the image, flip parts of the image. Flipping means here that we associate those regions with the mean of the image intensity. And again, this is, I think, a meaningful way to evaluate explanations, but it's not doing exactly counterfactuals. It's sort of an approximation to it, right? Because we don't have a causal model, so we don't know what that part of the image should be, and putting the mean value in is a poor approximation to this counterfactual question. But it does provide very nice evaluations, and also favor these relations to human evaluation and so on. Let me just hit towards the end point to another use of this averaging. So last year, in 2019, there was this problem posed, and it was even exaggerated in several publications last year also, that just like we can manipulate adversarial attacks, can manipulate image labels. So if we have a neural network, we can make small changes to the image and then get a different classification. A similar problem is in explanation. So I can make small changes to an image and then get a different explanation than the true explanation, so to speak. So this was posed as a serious issue for ethics, referred to as fair washing, that we can, if we have a system that operates by unfair features, we can sort of manipulate the explanation so that it looks more fair, right? So that's fair washing, the concept. And what we show in this workshop paper from last year is that exploiting the epistemic uncertainty, which is a fancy way of saying that we average over models, we get resilience to watch that problem. So you can see that here on the right side, we have an image and what we call a target image. So we try to manipulate the original image very lightly so that the explanation becomes that of the target image instead. So you can see layered relevance propagation, guided backprop, and saliency mapping. The original explanations in the first column, then the target explanation that we're trying to manipulate it into is in the middle, and then the manipulated explanation is on the right side. So you can see that it's very successful. We basically get the explanation we're asking for. So it is possible to manipulate. Not so much though if you use the aggregate. So here we have aggregated these into to sort of like an average from the three methods. And you can see that if we try to manipulate that, it's not very successful. So what it means is that it's harder to manipulate three different explanation methods than just one, right? Which is also what you would expect. So I think we can claim that we have some resilience by model averaging. And of course, the more models you average, the more you'd expect this resilience to be persistent. So let me go to going too much over time. Machine learning is not a black box, but that does not mean that we have no issues. So I've already hinted at a number of these issues, and there are many issues that we still need to understand. So the thing that I think is the topics that I think have been solved is this functional visualization. Decision level explanations is much harder, of course, and there's these issues with causality and counterfactuals. I think we have ways of quantifying uncertainty, and what I would say is more lacking are ways to communicate that in an efficient way. If we look at model averaging, as I've been arguing, it does improve performance. So you to average over different explainability schemes will provide better alignment with human annotations, for example. And also it will make your model more robust against attacks, like the fair washing attacks, for example. If we look at the open problems, I'd say that evaluation protocols is definitely an open issue, especially if we talk about this having humans in the loop. So taking human competences into account is really not explored very deeply. And then true counterfactuals would require causal modeling. So this means that we need an interactive system where you can interact during training also, so that the model understands what happens if you change parts of the image and so on. So by this, let me thank you for your attention. And of course, I'm very happy to discuss this both now and also later in the day if there's an interest for it. So thank you so much.